This is going to be the last lecture of this course, so I want to take this time to look beyond this 451 and briefly talk about what we learned so far and how we applied it to some knowledge later on. Okay, so one application of what we learned is in math finance. I already explained in the last week of the optional lectures. Okay, so it's extremely useful in math finance in defining the Brownian motion. And you can define these what they call the ethos integral, basically use integration in respect to the Brownian motion. So in this lecture, I want to take this time to talk more about the pure math side of the application. So let's start. So one thing if we recall, our original motivation of studying all this measure theory is really coming from the Lebesgue measure. So one property of the Lebesgue measure is that it satisfies this really nice property of translation invariance. So if I have a measure of, if I want to measure the X translate a set A, then it should return the same measure as A. We saw this really cause a lot of trouble because once you have this condition, you cannot define it on the power set of R. Okay, there's no such measure, so you need to define all these notions of sigma algebra and so on. But I want to briefly talk about these conditions, these translation invariants. So in general, if you treat R, the real, as a group, well, this is really just saying the group acting on the real line itself. Well, the Lebesgue measure is going to be invariant under this translation. Okay, so that gives us some notion of invariant measure. Okay, so suppose I have some group G. So instead of real, let's think about the group G, and it acts on a space. Okay, so usually we assume it has some topology, but it's just a set X. So a group action is basically defined as a map where each G will act on X. So you think about the classical one is basically the real line. You think about it as time. And the X is, for example, how the stars move around each other. So you have these translations. So as time moves on, the time will act on each point and then move the star to the next point. Okay, so that's kind of the idea. Okay, so this is usually called a dynamical system. So a dynamical system, basically you have a group acting on some space, and suppose you have a measure mu on some, let's forget about the sigma algebra here. Let's just say mu is a measure on X for some sigma algebra. Well, this is called G invariant if it satisfies the following condition. If you consider, if you want to measure G translate some set A, well, then you get mu of A. Okay, so it's basically the same thing as if you think about the R translate the real line itself. Well, then the Lebesgue measure is essentially just R invariant. It's invariant under this translation. So the study of these invariant measure are actually super useful, and it goes to this really big theory called the ergodic theory. So if you're really interested, well, that's one thing you can learn. I'm not sure Waterloo has any course on this, but it's a very useful theorem related to all these dynamical systems and finding the invariant measure. And once you have something that's ergodic, then, well, those have some nice properties, then you can talk about many useful results, okay? So I'm not going into too much detail, but I want to focus on one thing is that when G is a group acting on itself, okay? So when G acts on itself by this left translation, so that's basically G dot H is just GH inside G, okay? So every group will act on itself. Well, then you can have these, you can ask the same thing. Does there exist a invariant measure under this translation? Okay, so here's the definition. It turns out usually they exist, assuming you put certain conditions. So this is actually called a Haar measure, or let's say a left Haar measure. So a left Haar measure is essentially just a measure mu on your group G, so that the mu of a set A, well, A is some subset of G, and if you want to translate it, well, then you get is equals to the mu of A. That's for every A in, well, every G in G and every A inside some sigma algebra. Usually you do the Brown sigma algebra on G. So to have a Brown sigma algebra, you need to have a notion of open sets. So group on its own doesn't have a notion of openness. Okay, open is a topological condition. So usually you want to put some topology on your group, and that's what we call a topological group. So this G needs to have some topology on it. So you get a topological group. And the analysis of these Haar measure, well, it turns out under some mild condition, they are always exist. And in fact, there's a big theorem. So if your G is compact, then there exists not only a Haar measure, but there exists a unique Haar measure that's left and right invariant. And not only that, the mu is actually a probability measure. Okay, so the mu of the whole thing will equals to 1. Okay, and it's left and right invariant. So mu of, if you translate on the left, is the same as you translate on the right, and it's the same as the measure itself. Okay, so this is a big theorem. So all of these will be studied in something called the abstract harmonic analysis. Abstract harmonic analysis. So one course in Waterloo is the PMATH 833, which I just want to advertise a little bit because I'm actually teaching that next term. So if you've taken functional analysis already and you've taken this course, you're ready to take PMATH 833. It's a graduate course, so we're going to go over how to do these measures on these topological groups and study their structure and their the operator algebra arising from there. Okay, so that's one interesting direction. And if you want to go further down along this road, in our department, Professor Nico Sprank and Brian Forrest, they're really expert on this field. Feel free to talk to them. Okay, I'm pretty sure they like to talk about this direction with you. All right, so that's one direction. So, but I want to point out one immediate application is the following. So if a lot of these groups come from subgroups of the matrix groups, and they're called the Lie group. Okay, so this is not my group, but Lie, L-I-E. Okay, so Lie group is, well, the classical Lie group is essentially some topological subgroup of the matrix group, the invertible matrix group. And one of them is the unitary group. So I want to explain a little bit on this unitary group. Well, we can show this is compact. Okay, unitary, all the n by n unitary matrix is a compact group. So there exists a unique probability measure. So let's say mu, a probability measure on these unitaries. Okay, on these un. Well, these probability measure, well, one way you can think about it is as if this probability measure gives you a probability of randomly picking a unitary matrix. Okay, so if you want to say, how about let's pick a random unitary matrix? Well, what does it mean by random? Well, you use this Haar measure or this unique probability measure on the entire unitary space. And this is called the Gaussian unitary ensemble. Okay, so Gaussian unitary ensemble. So basically, you treat the unitary group as some measurable space with this unique Haar measure. So this is called GUE. And this is closely related to this theorem called the random matrix. Okay, so essentially you're picking a matrix at random, but what do we mean by random? Okay, so you really mean you're picking respect to a certain probability measure, and this is given by the unitary. And random matrix has a really long history in mathematics. People study random matrix. For example, they study the asymptotic, the eigen distribution. So they have really nice result and a rich history. And I want to briefly talk about this connection to something called a free probability. So let's talk about free probability. So what is a free probability? Well, the idea is the following. So let me briefly talk about this. Suppose you have, let's say, omega is some complex space, And then you can consider all the continuous function on your compact space, and you can consider its dual space. There's one result we didn't prove in this course because we're out of time, but this is the dual space is actually isomorphic to some class of measures on this omega, and when omega is compact, you can well, this is basically certain nice measures. Okay, you have some nice property, and don't want to go into too much detail. But one thing is the following. So one thing is that if you have a mu, which is a probability measure, then what you can do is you can define a linear function on your continuous function on this omega. Okay, so you can define something called phi of mu in a very similar way from c of omega to the reals. So if I give you a function, you return the integral of this function in respect to this mu, okay? So I kind of put this on your last assignment. If you recall your assignment 10, the last question is something similar than that. You have mu is the Dirac measure, and you do the integral, and I ask you to show this is actually a continuous linear functional. In general, it's always the case. You can integrate respect to any probability measure, and you get a linear functional. And one thing about this, nice thing about it is that this phi of mu, okay, so first of all, is inside the dual space, or it's a linear functional. And it also maps the constant one function to one, okay? But it also has a nice thing. So one thing is about this classical probability is that things are commutative. So if you take two functions, f and g, well, then they are commutative, so they're just really g and f, okay? So they're always commutative. But is there a way to generalize this continuous function on some compact space to some other algebra, okay? So can we generalize this to something else, okay? And it turns out that's kind of the idea behind the free probability. So the idea of free probability is the following. So suppose you have some A, which is a non-commutative, and let's say it has a unit, so let's call it unital, some kind of algebra, okay? And if you learn functional analysis, this is actually called a von Neumann algebra, or there's a course about operator algebra after functional analysis you can take, and you learn these von Neumann algebras, but that's where it's defined on. And basically, you can think about a continuous linear functional from the dual space on this A, well, A to R, or actually usually you go to the complex. But this looks like a probability if you're the phi, if you map the constant one function to one, and if you map some f positive, well, if f is positive, then you map it to something positive, okay? So this phi will look like, okay, it looks like a probability, okay? Probability, all right? So this is kind of the idea behind free probability, and this theory is fairly recent, actually developed by Dan Wojciechowski. Okay, so he developed this idea of free probability. And a lot of the classical probability theory talking about, for example, in the last week, I talked about independence. They have a free analog in the free probability. And a lot of the classical probability theory, for example, the central limit theorem, basically says if you have some identically distributed things, you take the average, they will converge almost surely to a normal distribution. This also have an analog. Okay, so the main theorem is they have some notion of the free central limit theorem. So if you take some freely independent random variables, they're no longer commutative, but then you can consider their central limit theorem. You can take their average and you say what's the probability. Well, it basically means you throw it into this linear function of phi and you compute it. And it turns out they converge to a free central limit is the semicircular law. I'm not going to talk too much about it. But it turns out the free semicircular law is kind of known in the probability theories when they study the random matrix. And it turns out this has a really nice connection with the random matrix theory. Okay. So one way to think about it is if you randomly pick a bunch of matrices, then their eigenvalue, they're kind of asymptotically looks like a freely independent random variables, and you have these connection. Okay, so these connections are a very active area of research. So one is free probability, and the other is random matrix, and they are often related. You probably already know in our department, Professor Andrew Nika is a PhD student of Danwood Class School, and he's really expert on these free probability stuff, and he's mainly interested in these combinatorial aspects of free probability and random matrix theory. So feel free to talk to him. Okay, I'm pretty sure he'll like to talk about these. All right, so now I talk about a few directions along these Haar measure, and let's briefly talk about one more thing. There's one other way to generalize the measure is the following. So if you consider a measure, well, a measure is essentially defined on a sigma algebra to the reals. Well, of course, you can say, let's talk about sign measure or even complex value measure. But what prevents you going even further? How about the matrix valued? Okay, so matrix valued, or if you learn the function analysis, you probably know matrix is just finite bounded linear operator between Hilbert space, where your Hilbert space is finite dimensional. So you can think about a bounded linear operator on Hilbert space. Okay, so it's called B of H. Okay, so these are called the positive operator valued measures, so positive operator valued matrices. Okay, so POVM. Okay, so why they're interesting is because they are closely related to quantum mechanics. Let me briefly talk about their definition. So first of all, your measure usually we require measure to be non-negative, and in the positive operator value, well, your mu of a set E is now a matrix, an n by n matrix. What does it mean by a matrix to be positive? Well, usually it means the positive semi-definite. Okay, so it's positive semi-definite. Okay, so in particular, it should be self-adjoint. Okay, so self-adjoint. And that's basically replaced the mu being positive. And usually, well, in POVM, in the quantum mechanics, you think about it as a quantum experiment. So you want your thing to mimic a probability, the classical probability to the quantum probability. So in the classical sense, your measure is a probability measure if it measures the entire thing to 1. Okay, the mu of x equals to 1. While in the quantum case, if you want to measure the whole thing, well, what's 1 in your matrix? Well, it's just the identity matrix, the n by n identity matrix. And finally, you have some thing called a sigma additivity. So the classical case, you have a sigma additivity, and in the quantum case or in a positive operator value case, it's basically the following. So the sigma additivity, this is some idea if you take in some quantum mechanics. You probably know this if you take any vector inside, let's just say everything is n by n matrix, you take a n-dimensional vector that kind of corresponds to a experiment. Okay, so you have some matrix you evaluate on this phi, and then you take the inner product. Okay, so this is kind of you measure these quantum states with respect to this phi. So now you have basically a map. Okay, so you start from a map E from your sigma algebra D, and you map it to this value. Okay, so you want this one to be sigma additive. Okay, so this is what I mean by sigma additivity. And if you satisfy all of these conditions, then you call it a positive operator valued measure. And this is, I probably don't need to tell you, but this is quantum mechanics is really mechanics. It's a really active area of research. We have a whole building dedicated for that. So if you talk to in our department, Professor Vern Paulson, and also I'm pretty sure there are some new faculty from the quantum department, they will be happy to talk to you about some generalization on this line. All right, so I guess that's all I have. Okay, so I really hope you enjoyed all these courses, and I really hope this major theory will be useful for your study later on. Okay, so that's everything. Thank you for listening.